Sound okay? I don't want to. Everybody finished? Shall we start? All the work handed in? Okay, so what I will, before starting to talk about strong lensing, I will briefly go through the answers to the exercises I said to you last night. And these exercises, if you can do these, then the homework today, then the test of today was easy. So the first question was this singular isothermal lens with an Einstein radius equal to 1. And I gave you the source, was at position 0.7, 0.7, and had a certain size. And of course these coordinates are such that it falls almost exactly on this Einstein radius of radius equal 1. And so the question is, this is the source, where are the images? Now, the singular isothermal lens, remember, has a deflection angle which is constant, so all images are always exactly displaced by the same angle. Alpha is also the Einstein angle, therefore. And so what this means that wherever you put a source, wherever you see an image, rather, this is an image, then you know from the lens equation that the source was exactly PTE further in along the radius vector towards the center. That's what the lens equation tells you. Source position equals image position minus deflection angle, and in this case the deflection angle. So if you have a source, if you have a different image here, then you get a source. So this gives you a source. And so the question is, what happens to all the various points in this large source here? Where do they all, in this source here, where do they all form? And so one thing is clear, which is that if you go outwards by theta e, all these points, if you move them in by exactly alpha, by exactly the bending angle, will fall on the source. So all of these points are certainly image points which, when you map them through the lens, put on the source. So that's one part of the answer. All of these points in the image plane come from this point, from these points in the source. But if you think about it, there's also more solutions, because if you imagine having a point very close to the, you have an image very close to the center of the lens, again, that image is lensed by the same lens equation. It's moved by a distance theta e towards the center, and in this case, because it's closer than 1 to the center, it actually moves to the side. So the source that corresponds to this image here actually lies on the other side of the lens. It's the same angle, the same unit that you move the light rays, that you move to go from the image to the source. But so this shows you that for images which fall inside the Einstein circle, there's also a source on the other side. So the sources that fall inside the Einstein circle, there's also an image sector. And so part of the source actually corresponds to a kind of image like this. These points here, which are on the Einstein circle, are actually part of the image of the source right behind the lens. And then this part of the curve here is part of the source which falls inside the lens. So this is the image that you get from a singular isothermal sphere when you put a source right on Einstein. So you get an arc outside the Einstein radius, and it's kind of squeezed in this direction because the transport is not parallel, but it stands out. It's a long radial vector. And you get the second part here, which connects to the center, which is the second image. Just out of curiosity, how many people got something like this? I won't give any numbers. Okay, the second question was a different lens. Now I gave you a potential which is now slightly more complicated than what you have for a point mass or a singular isothermal sphere. And so this is really a direct application of the lensing equation. Where if I give you a lensing potential, the displacement, the lensing angle is simply given by the gradient of distance isolation. And so I gave you 4 potentials. And I simply gave you the 3, 0 was the image position. You simply work out what the gradient of the potential is at this position, 3, 0, subtract it off. And if you do that, you end up with a very elongated image, the source rather. I have a picture of it somewhere. In fact, I can show you this. So this is the answer to question 1 that I just described. I can also show you a little movie that shows what happens when you move the source. So this is the Einstein ring. This is where the source is. This in blue is the images that you actually see. So the source is in red, what you would see when there was no lens, and blue is what you actually see. So you see that the image is always further outside. It's always displaced by unit, by the Einstein radius, and then as soon as the source touches the Einstein ring, then the second image starts to appear. When the source is right behind the middle, you get the full ring. Now it's again outside the Einstein ring, you just get a single image. Okay. Then this was the answer to question 2. So this is where you have this square that you have to remap through the lens equation to the source plane, and you can't see the coordinates here. the answers were something between 1.8 and 1.9. And then question 3. Question 3 was a lens potential. It was an elliptical potential, right? X squared plus 2y squared you have here. And the question is, what do the critical curves look like and what do the caustics look like? This is simply the calculation we did yesterday, where you work out the distortion matrix 1 minus and you take the determinant of this matrix equal to 0 to find where the critical curve. And so I can show you the full answer, which is this one. So in black here you see the critical curve. And I asked you to calculate a few special points along the x-axis and the y-axis. But you see the critical curve is kind of an elliptical. And then when you map this back to the lens plane, to the source plane, then you get these caustics. So I hope that these fairly simple calculations worked for you and that you were able to get there. Yeah. Any more questions on this? All right. Then we go to the lecture for today. And today we're going to focus on the case of strong lenses. So the strong lenses are the case where you have these critical curves, you get multiple images, and you get very complicated image structures. Where's the eraser? I need something to clean the blackboard with. I'm not going to do it like this. Okay, never mind. So let's see how far we get. With strong lenses, they're kind of the examples. Whenever you Google gravitational lensing, then they're the kind of examples that you see. And so, for example, you can imagine astronomical applications, but you could play games with strong lenses any way you like. So let's take a photograph, for example. Here's I don't know if you recognize this picture. This is in Washington. This is a castle on the Mall in Washington. So here is a nice photograph, and what we can do, we can imagine what would happen if we put a gravitational lens right in the middle. What kind of distortions would you get? Infinite magnification in the tangential direction, very strong distortions. You see that at large distances from the center of the lens, you get a little bit of distortion, but not very much. And you see that in the middle, inside the Einstein radius, inside the critical curve, you see repeat images. You see multiple images of things which you also see outside. For example, you see the two towers again. They're very distorted. The other towers here. This here is a part of the path, etc. So this whole area inside here is actually second images of the rest of the sky. So this is exactly what the lens has done. I told you that lensing is a kind of repulsive effect on the sky. And you can really see this happening in this photograph, that it's like you put a lens in the middle and you've pushed all the pixels of your photograph out towards the outside of the, away from the middle. And then the space that you have in the middle, you fill up with extra images of your sky. And you can do this with many pictures, and you can get very crazy things. For example, this was my boss in Leiden, who when he retired, this is the present that I gave. I put a gravitational lens in front of his face. I never quite got around to putting good sound effects with this. It's actually the same lens. It's also a point lens, and you can see again the same thing. If you look at any of the frames, and you see in the middle that there are second images that actually suddenly have two bosses. So you can do these things for fun for as long as you like. And so the principle is really very simple. It's really this lens mapping that you have. Simply, you start with your picture, and you move all the pixels with this very simple transformation. And so what we did yesterday was we talked about how this lensing equation comes, what this lensing potential means, and how you can relate the lensing potential to the distribution of mass in your lens. It's gravitational lensing, so it's to do with mass. Now what we're going to talk about in strong lensing today is mostly axisymmetric cases, so round lenses, and then there's a few special relations we can use. I still have to derive those. And then we're pretty much done with the mathematics for today. So we have the Poisson equation, the lensing potential, the del squared of the lensing potential is twice the surface. So in spherical, let's take polar coordinates because everything is spherically symmetric. So in the θ1, θ2 plane, I'm now going to define coordinates theta, which is the modulus of the vector, and I'm going to define the polar angle chi. So I'm now defining angles in an angular plane. It's a bit confusing. It's just polar coordinates, distance to the center of the lens, angle. And so for an axisymmetric lens, the potential and the surface density only depend on theta, not on the angle. And so therefore we can write the Poisson equation just in polar coordinates. So this is what you would know as 1 over r d by dr. R d by dr, except now the radial coordinate is theta. And we can integrate this up. And get theta d phi by d theta. Right, moving over here and integrating. And this, let me write it down first and then explain it. This expression k theta integrated is really just the total integral of the surface mass density within the circle of radius. If you put in this pi, then you get the usual 2 pi r dr. And so this whole integral is simply the total mass enclosed within the disk. Total mass. And another way to write this is to say that it's the area of the disk, the average surface density in the disk. lens, we get a very simple relation between the gradient of the lensing and the average mass density within the radius. And so this, of course, is alpha. So what this tells you is that for axisymmetric lenses, the bending angle that you get is simply the product of the size of the disk at which you're measuring the bending angle times the average surface mass density within the radius. So this shows again that you're really measuring masses directly if you can measure them. So that's this result here. This is only valid for axisymmetric lenses. And the second thing is we can also relate the shears to the potential in an axisymmetric section. So if you remember, the shear was d by d theta 1 squared minus d by d theta 2 squared of the potential. And then the second component of the shear is the cross derivative. Now when the potential only depends on the modulus, then you can simplify these formulae because first derivative simply becomes theta 1 over theta times the gradient, the radial gradient. So just taking the gradient in the x direction and projecting it into the gradient along the radial direction. So the second derivative, now you have to differentiate all of these three terms separately. And you end up with this. Right, so this is the derivative when you hit theta 1, this is the derivative when you hit 1 over theta, and this is the derivative when you hit d psi by d theta. I'm not going to spend too much time going through these derivations. They're a bit messy but not very complicated. Just that if you take this and you do the simplest thing for the d by d theta 2, then you get an expression gamma 1 which turns into similarly for gamma 2. And so you see that gamma 1 and gamma 2 have the same factor here, the same dependence on the potential, and this is just a geometric angle. So this is actually this is the cosine of twice this chi angle. And again, I'm not going to spend too much time going through all these derivations. And so what this shows is that gamma 1 and gamma 2, and this is kind of what you expect by symmetry. So if chi is 0, then you're on this side of the lens. On this side of the lens you have a gamma 1 which is non-zero and a gamma 2 which is 0, so you typically get something like this. Up here, chi is equal to 90 degrees, so 2 chi is 180, so here you change the sign of gamma 1 and gamma 2 still stays 0. So that gives you a shape like this. And then here we go back like this, and here we go back like this. And in between at 45 degrees, then cos of 2 chi is 0, so gamma 1 is 0, and sine of 2 chi is equal to 1, so then you just have the gamma 2 term. And so we can write the shear as what we call the tangential shear times where this tangential shear is just this. So this is kind of messy, but in the end what you end up with is you get an expression for the shear, which is just one number instead of these two components, 1 and 2. And all that happens is that as you go around the lens, orientation of the shear changes, but the shape stays the same, the magnitude stays the same. And this is what you expect by axis symmetry, that it doesn't matter which direction you look, the effect should be. And then if you compare these two expressions, so this is from the del squared and this is what we just derived. The difference from these two shows you that gamma is simply the difference between the mean kappa, here, and the actual kappa. So in other words, the shear measures to what extent you have more mass, more surface mass density inside your radius than you do at the radius of the human. It's a mass contrast. Surface density contrast measurement. All right. So again, this is, if you like, it's just mathematics, but it's again a recipe. If I now give you an axisymmetric lens, and all I give you is the potential, the dependence of the potential on angle, or I give you the bending angle, so that you can work out the potential by integrating it. Then you have all the information that you need to work out what the convergence is, what the shear is, and in the end also what the magnification is, your distortion matrix. So you can find all the critical curves and everything, again, by applying these simple recipes. And so all these things are derived in detail in the book 1 and 2 from the SAS matrix. And so, for example, you can consider all kinds of toy models. So any surface mass density which is axisymmetric will give you a lensing potential, which will give you the shear, and which will therefore give you the critical curves, the lensing equation, magnification everywhere, etc. And also even the thermal. There's nothing to stop you from doing an axisymmetric lensing Cartesian coordinates if you want, but of course this is much more complicated. Okay. Now there's one. Can I wipe this? Before we go to showing examples, actually, let me just show you the example. There's one other thing which I have to show you, which is a limitation of lensing, which is called the mass sheet degeneracy. This is the last piece of mathematics that I'm going to give you today. So if you remember, lensing equation. Then now this is a transformation of the lens, which leaves all the images in exactly the same place. In other words, on the sky, you cannot see the effect of this transformation. And it goes as follows. By this equation by some constant k. It's completely arbitrary. You can choose any number for it you like. And we then try to take this equation and we rewrite it. We try to make it look like a lens mapping. We try to make it look like fairly trivial. I've just turned this k theta back into a theta by adding this term here. And now I'm going to write this as gradient of a new potential, which is k times the old potential plus something that gives me this gradient. And in fact, all of this is in all of these are vectors again. And so this shows that if theta is a solution of this equation, right, if these are images that are part of that I'm seeing in my lens, then these same theta are solutions of this equation, which means that I would also see these same images through this lens, through the lens with this potential. So this new potential here is the old potential scaled by a certain factor plus something, which is what's called a mass sheet. Because if you work it out, and it has a surface density which is constant everywhere. It's just 1 minus kappa. And so all I've done is I've changed the potential by a certain amount and I've changed the source position by a certain amount. So what I've done is rescaled the source plane and modified the lens plane. And so because we usually don't know what the source plane looks like before the lens happened, we don't actually know how large the sources are, so this is an uncertain thing. It might be that we're looking at a galaxy that's half as large, in which case we can put in this k of 2, for example, and we would see exactly the same thing. And so what this shows is that if you have a lens system, you see a quasar which is multiplied or imaged 4 times, for example, through a lens, then you can work out the lens, but in the end, if you work out a lens model that explains all the observations perfectly, then you can, through this formula, make a whole family of lens models which will look absolutely identical on the sky. You'd have to move the quasar a little bit by this factor k. You'd have to modify the potential by this amount, but you would get exactly the same lens configuration, same configuration. And so this is valid as long as you don't know the size of things in the size. Now you can break this degeneracy in various ways. The simplest one is to simply forget about it. That's what most people do. But if you really want to break it properly, then you can say you expect that at large distances the lens has 0 surface mass density. The lens is 0. Whereas in this mass sheet at large distances, the mass density goes down. So if you have information at large radii, then you can pretty much limit the flexibility that this gives you. But if you only have information in the center of a lens, for example, the center of a galaxy that's split in the light of a quasar, you actually don't have much constraints. So you can assume. So very often this is actually a real constraint. And the other way you can break the degeneracy is with time delays, which I'll talk about in a little bit, related to the Fermat. Okay. So this is something to bear in mind when you're doing lens modeling that there's always this ambiguity. Okay, so now let's talk about, this was all axisymmetric lenses, now let's go to elliptical lenses. We very quickly run out of cases where you can actually do calculations because you just get too messy. So instead I'm just going to show you pictures that show you exactly what happens in case some specific example. So I'm going, this is again from the book, book B2, if you read the sections yesterday. At the top here we have the source plane, so this is the caustic that we're showing. At the bottom is the image plane, so this is the critical curve. Now for a round lens, you never get this kind of diameter caustic, that's a sign of ellipticity. But sometimes is this radial caustic. And so what's shown here, I'm not sure how well you can see this, is the effect of moving a source. So this is the source which is moving out from far away through first the outer tangential caustic, outer radial caustic and then into the tangential caustic here. And here you can see the corresponding effect on the images. So what you can see is that when you're far away from the lens, then you just get a single image, but then as soon as you cut across the tangential caustic, you start to create 3 extra images here. And then in the end you get this full richness of up to 4 or 5 images. And here is a similar example where you now approach along the minor axis, the major axis rather, and you get the configuration on different sides. And here, what happens if you move the peg, you don't go through these clusters, but you go through the side of this. As the lens is very elliptical, you can get this situation where this dust actually sticks out of the radial caustic. So these are the kind of diagrams people use to interpret all the possible information, all the possible configurations of 4 image lens quasar. And here's an example where you can see almost all of these effects going on at once. So this is a very complicated lens now consisting of a large, massive concentration of mass here, plus individual galaxies, which are little perturbations to the big lens. Then in blue is a background screen of galaxies that's being moved behind this foreground lens, which consists of the dark matter and the galaxies that we see in yellow. So what you see here is all the effects that we saw before at large radii. You get the gentle pushing away of the sources from the lens, but no tremendous distortions. When you get closer to the lens, you see this area where clearly there are very large magnifications going on. That's the critical curve associated with the Einstein radius. And then the other thing you see is that there's another region here where images appear and disappear. And these images are not stretched tangentially like they are along the critical curve here, but they're stretched radially. And that's this radial caustic that you get in the middle of lenses. So if you follow a single pair of images, you see always that in this region images are created as a source moves across the caustic in the source plane. Created, they split off, then they move in separate ways, and somewhere else they annihilate again. So try to follow a specific. Try to follow this guy, for example. Annihilates again. Any of the radial sources that split off, they go their own way and then they meet up somewhere else and annihilate again. So that by the time the source is far away from the lens, you end up with just a single image again. And you see here that in the middle, images are always created or destroyed in pairs. So that means that there's at any one time always an odd number of images from any single source. One more time.
And which kind of distribution of assuming here? They are assuming that each galaxy in the cluster is producing its own field and
each galaxy in the cluster has its own, and then there's also a big concentration of mass sitting on the center of the cluster, kind of big dark. It's meant to be quite realistic. And also the fact that you get these very long tangential arcs sometimes, demarking really. So if you see this, supposing that this is a real observation and you see this in a telescope, you can immediately learn from this what the total mass is inside this circle. You can say this is clearly the Einstein radius. Looks like it's approximately an axisymmetric lens, the first order. So here is the Einstein radius. So that means I know that all the mass inside this radius is causing a deflection that's enough to move the source right behind here. This is the source right behind here to turn that into a very large. So that's actually one of the most accurate measurements of masses that we have in cosmology. Only for this one specific region inside the Einstein radius. If you want to know how much mass there is here, it's much more difficult. If you want to know how much mass there is here, it's much more difficult. But just the Einstein radius gives you this very accurate, very precise anchor point.
Can you put it again?
Yeah.
Just to see.
Do it the whole day.
So it seems that the Einstein radius is variable.
So it's not a perfectly axisymmetric lens,
Okay.
which is why you get some perturbation. For example, this is a nice case. Here is a little second halo, second mass concentration, which feels a little bit about this lens, but not very much. Whenever a source comes nearby, you see it's nearby. And the effect you get is always more or less the same. It's really the idea that the light rays are pushed away from the mass concentrations because they have to make their way around them. You see this with all these galaxies here. You will see that when a source comes behind them, either wrapped around it or just pushed away. These guys, for example. So one other thing you can say, this relates to the weak lensing chapter that we will discuss on Friday, is that if you, in here you see all these funny image structures and distortions, but out here you don't really, just have one snapshot, you don't actually see very much. You don't automatically see that you're close to a lens, but there's actually a lot of lensing going on also in this part of the diagram. But nonetheless, if you were to analyze this, if you were to look at all the shapes of all these individual little galaxies, you would see the tendency for them like this, not like this. And that shows that there are some average shear. You really are measuring one of these shear components here. You cannot see it galaxy by galaxy, but you can see it from the ensemble of the whole population of galaxies here. If you were to do the same thing here, you would see that they're more or less aligned like this. In this corner, you're a bit closer to the lens, so it's a bit stronger, and clearly things are aligned like this. So you can actually get statistically also more information out of this than just close to the Einstein radius. And that's what the whole topic of weak lensing is all about. Okay. Now, yesterday we ended with this Fermat potential. Right? This Fermat potential is a way of describing the whole geometry of lens formation. So I have a bunch of movies that show how this Fermat potential behaves under various conditions, and it's quite instructive, I think. So all of these cases are for lenses very similar to the ones that you were playing with in the exercises yesterday. The logarithmic potential with a flattening parameter q in it, and I play with the amplitude a. So in this case, if you remember, the Fermat potential is a quadratic plus the lensing potential. And the use of this potential is that the lensing equation is equivalent to the stationary points of this potential. So you pick a potential, you pick a particular position for the source, and you can construct this surface, and then you look for all the stationary points, that images will fall, because those are the points that solve the lens equation. So here's a case where at the moment the lens is still switched off, a is equal to 0, so you just have this parabolic first term part of the potential, e to minus b squared. And I've put the lens right in the middle and the source right in the middle, so that is equal to 0. So now let's see what happens when we slowly turn up the amplitude of this. That's the phi that you're adding into the middle, right? So potential usually is negative, but because we're subtracting it, it actually gives you. And so what you see is that at some point, remember that the images are formed at the minima or the stationary points where the gradient of the surface is zero. So you see that in the beginning, when there's no lens, clearly the minimum is in the middle. The minimum remains, the middle becomes a maximum, so that's still a stationary point. It's still a position where you form images. But you also get this ring around here where images are formed, and that's the Einstein. So all around here now you have a region which is the minimum of this Fermat potential. Therefore the gradient is zero there, therefore it solves the lens equation, and therefore you get images. Now this is a fairly trivial case because everything is perfectly symmetric. But if we go to, first I can show you the same thing in the image plane. So this is now not as a surface diagram, but as a contour diagram. It's the same Fermat potential. The cross in the middle is where the center of the lens is. Contours are the contours of the Fermat potential. And as you turn up the lens, then again you see this peak appearing in the middle. The darker this, the higher this one. Think of it sticking out of the board. And then the minima you see here. And in blue, I've shown you the location of an image, of the image of a source that I've put here in the middle. So this shows that the sources are indeed at the stationary point. Okay, let's make it a bit more complicated. Let's go to an elliptical lens. Here again, the lens is switched off. And I've put the source again at beta equals 0, so the source is right behind the middle of the lens. Let's switch on the lens. So something very similar to what before happened. Again, you raise the peak as the amplitude of the lens increases, but now you don't get you still get a maximum in the middle, so you would form a faint image here. But now you don't get a nice ring of minima, but instead that ring is broken up into a saddle point, minimum, another saddle point, and another minimum behind you. Right, so instead of it being a ring, because now we don't have the symmetry, the ring has broken up into a number of stationary points. And so 5 stationary points means 5 images. So in this case, this shows there are 5 images in this elliptical lens with the source right behind it. And the 5 images are 1 in the middle, 1 at these 2 minima, and 1 at these 2 saddle points. So you get a perfect cross. This is what an Einstein cross is. And the other thing to remember is that the magnification depends on the determinant of this distortion matrix. The distortion matrix has the terms which are basically the second derivatives of this potential. So in the cases where the potential is rather flat, where the minima are very broad, you get a very strong magnification. Here, where the second derivative is very large, you actually get a very strong demagnification. So this source is going to be very weak. This image is going to be very weak. These images are all going to be quite bright. And I can show you the same thing in the source plane. Again, lens switched off, switch on the lens. You now see very clearly, because the potential that we're adding is elliptical, you see now that there are these 2 minima and these 2 saddle points, and we kind of have to go over a hump to get from this minimum to this minimum. So these are now the locations of the 4 bright images, and there's a very faint image here in the middle also running across the board. And now let's break the symmetry completely. Let's also move the lens away from the source. So let's not put the source right behind the lens anymore, but put it a little bit to the side. Then you don't actually see much difference in the surface plot. But here, if you now look at let's now put the source over there. Lens over there. You see we're now pushing this lensing potential in the middle here. It's not in the middle of this parabola centered on the source. And so it's a symmetric situation. It's kind of a perturbation of the previous one. It still gives you 4 images, of which 2 are saddle points and 2 are minima. And there'll be another one here in the middle also.
Einstein X.
Yeah. And so if you move this lens further away again, then you will see that these three things begin to move together. At some point, the saddle point and this minimum will annihilate and they will disappear. So, so this is what happens. So now I've done the same calculation, but now what I'm doing is I've left the strength of the lens at the maximum, and I'm going to move the lens over. So the source is in the middle here. The lens is at the moment centered here in this plot. So you see that the image has already moved a little bit away from the center. And now I'm going to move this lens here. Now you see very nicely that new images come and go and they annihilate with each other. And you also get a feel for how this is really completely geometric and topological. And all this is this parabola that we started with here. And you're flipping that parabola by pushing. It's like making a sheet, and you're pushing something underneath the sheet and changing the shape of it. And so you see here, this is a radial image creation, and this is a tangential image annihilation. So, and you can play with exactly the shape of the lens and exactly where you put the sources. So there's a very long variety, very strong variety, and exactly how many 5-point images. If you want to make more than 5 images, you have to make lenses which have a lot more ripples in them. So this is really the most general, reasonably smooth lens that you can play with. And so the amazing thing is that there's actually a lot of lenses like this in the sky. So this is a little compilation. These are 9 quasars, each of which are sitting right behind the galaxy, which has an elliptical shape. And so it's doing the kind of lensing that we just maybe a little bit too bright here. You see, often you can see a blob in the middle. That's not the fifth image, that's very faint, but that's usually an image just the lens. It's the galaxy doing the lensing. And then here you see very nicely 4 images of the quasar. Here you see a very nice, almost symmetric situation. Here you see a case where 2 of the images are very close together and the other 2 are further away. So if you move the lens a little bit, these 2 might annihilate completely or they might separate. So you see more symmetric. And so all these cases are able to be modeled very simply with basically a very simple, smooth elliptical lens and not much.
The elliptical, sorry. The ellipticity in the potential is parameterized with this Q, right? You show an analytical expression for this Q, and you can plot this in Python very easily if you draw the contours, this potential. Okay, so the homework for tomorrow.
You want? You want? My computer is coming. Okay, I think we can stop here. What I will do after, in the second half, is talk more about the kind of applications in which strong lensing is being used. So we will talk about the use of the Fermat potential to measure time delays in some of these cases. If the quasar is a flash, then you will see this flash in each of the images, but not at the same time, because some of the light paths are longer than others, and you can use this to do cosmology. I'll talk about how you can measure masses of galaxies and clusters using strong lenses, and a few other things. Yeah?
Okay. ¿Alguna pregunta, muchachos? ¿Dando mucho calor? Bueno, mucho. Bueno. Nos vemos aquí a las 4 otra vez.